So it's 1 o'clock. First of all, are there any questions? Just speak up. Just speak up. Don't raise your hand or type. Just speak up. Are there any questions?
Hello, sir.
Yes, yes, yes.
Sorry, I just had a quick question. From the part we did last class, the disc.
Yes.
If we weren't to cut it and take sliders, surface sliders on it, is there an easy way to restrain it, like into
Okay.
the
Are you saying that if you did not cut it, is that what you said? Is that what you said? You did not cut it and you put it, you want to? Okay, listen, if you don't cut it, there is no surface to put a surface slider on. You know, if you made that whole disc exactly like it is, you don't have a surface. For example, you can put it on the top and the bottom of the disc, but you're saying that is not a plane symmetry because I didn't cut it. Therefore, it's not possible to put it. I mean, it's wrong to put it on the top and the bottom. And since there are no sides, you know, there are no slanted faces, then you can't put slider surface on it. Does that make sense?
Yes. So would you be able to like use a restraint a point?
That's going to be tough. You know, that problem, if you don't use symmetry, those side planes, if you don't have it, it's going to be harder to do because it's free to move as a rigid body. In the book, I'm showing you a way of doing it, but I don't want you to get confused with some of the subtle things that come up. If you want to see that, my suggestion is come in the office hour tomorrow or hang around after this lecture. It doesn't matter. It's just that without symmetry, it's going to be harder to do. Okay, without using those cut planes on the side, it's going to be harder to do. It is possible, but it's harder. And remember,
Okay,
please please remember on the test, we say use all applicable planes of symmetry. So in principle, if that problem was given to you on the test, cut. Now, we don't insist that you cut it with, I don't know, 45 degree or whatever, but cut it, something between, 30, 45, 90, etc. And then cut in the middle, of course, too. All right? Yeah. Okay, any other questions before we move on to the new stuff?
Yes, Professor.
Yes, go ahead.
I just wanted to know if there's a way of constraining an axis to a certain line. So let's say we have the y-axis and we've revolved the disk to form it, right? So
yes.
can we constrain the central axis of revolution to let's say the y-axis so it doesn't move as a rigid body? Is that possible?
You're talking about a single part. You're talking about a single part, right?
Yes.
A single part that we are doing this analysis. Right now, we're only worried about single part, okay? When you have a single part, when you create an axis, okay, that axis is kind of attached to the object. So I know what you're thinking. You're thinking about what if I had a kind of a thing that was stationary. That's what you're talking about as global, I think, global axis. So immediately it kind of becomes two parts. Okay, one for something that you don't want to move as a rigid body, and then something that is fixed in space. But you can't do that. Don't go that route. Just don't go that route. Okay.
Okay. I was thinking along the lines of axial constraints. So since that's possible when we're doing an assembly, I was thinking if that's possible also for analysis.
Well, remember, analysis looks at what you gave it. If you gave it an assembly, it's going to require several parts. If you gave it a single part, then of course we are doing analysis of a single part. There are other things to do. So right now we are looking at a single part, and what you have in mind, I don't think is possible, or actually, you need to do it in the context that you have in mind.
Okay, thank you, Professor.
Okay, so let's move on. The brand new topic. So let me remind you, when you took your deformable bodies course, probably Dr. Green taught you too, or when you took the stress analysis course last summer or last fall, when you were dealing with beam problems, you just drew a straight line. You just drew a line. You didn't draw the three-dimensional shape. You just drew a line. And then you said, okay, this line, for example, the left end of it is clamped. Say you have a clamped boundary condition. The right end of it is subjected to a force, okay? But everything was in the context of a line that you drew. Then at some point, you had to, somebody had to tell you, what is the cross-section? What is the cross-section of this, this beam, okay? What is the cross-section of the beam? Because you could not solve the problem, the beam problem, without the cross-section. Can somebody tell me, when somebody gives you the cross-section, what is it that you get out of that to solve beam problems? What kind of information do you get from cross-section? Just say it. Yeah? Can you say it?
What's been
See, I
mentioned
was,
so far in the chat is area and shape.
okay, let me, I was trying to avoid to go to the chat. The situation. If you try to do beam problems or create beam elements, we have not done that yet, okay? You draw a line, just like you did on the paper in your deformable bodies class. You draw a line. For example, you say left end is clamped, right end is subjected to a load. But this is not sufficient. Even if you said what kind of a cross section you have, for example, a rectangle like that, is it oriented like that? The second one from the bottom, is it oriented like the second one from the second one? Well, the third one from the bottom, is it oriented at a slant? So the moral of the story is, you draw a line, but just saying that the cross section is a rectangle for a three-dimensional calculation, not good enough. You need to say how it's oriented. Planar beam problems. But if a beam is oriented in space, then you also need to give it some information beyond the shape and the dimension. Give it information which tells you, is it oriented like that, or like that, or like that? Because each one of them will behave differently. The only case where you don't have to specify orientation is when the cross section is circular. Notice that if you turn the circle around 90 degrees, 35 degrees, it doesn't matter. It doesn't affect the response of the beam, because it's a circle is a circle. It doesn't matter how much you rotate it. But here, the behavior of the beam is different for that cross section, oriented like so, or this one, or that one. Okay, good. So the problem that we're going to be doing today is the same one that we worked out a few days ago. Feels like ages ago, but it was I think the first day of classes, almost yeah, almost 2 weeks ago. It was this bent rod, and I told you that if you wanted to find the deflection, remember the bent rod had the cross section which was circular, and then this bottom was clamped, and then we applied a load here so that it made this thing to twist, and bend. I said this is not the most efficient way of solving the problem. You know, I leave it like that, but I'll say a few words about this thing later on too. What is better is to create the structure, the part, as a curve like that. Just a curve, no solid object, just a curve. You draw a line, remember? You just draw a line like this and tell it that the cross section is circular, okay, which makes it easier because there's no orientation going involved. You can always, you know, just specify the cross section of or the area of the circle, radius of the circle, and then break it up into little elements. Little elements along this line are what are called beam elements, like that. It doesn't have any fancy three-dimensionality into it. The three-dimensionality comes from the fact you're saying what is the cross-section, okay? Now, each node, this is a linear beam elements, one node here, one node there. So this is a single element, one node here, one node there. Each node has 3 translations, unknown translations, and 3 unknown rotation. Now, this business of rotation and things like that is nothing new to you, because when you did beams, you calculated effectively 2 things. Vertical displacement, if it was a planar beam, transverse deflection, vertical displacement of the beam, and rotation at a particular point, the end of the beam, or whatever you want, okay? So this business of rotation and displacement was also appearing in the skies at the degrees of freedom when you took your deformable bodies course or strength or stress analysis course. Okay. All right. So let me go ahead and do this problem 2 different ways. Okay. I go here, start with a part file. Part file. Say okay. Immediately I save it. File, save management, save as, desktop. Where's my desktop? Desktop, new folder. I'll say May 20th. So this is section 1, lecture section 1, 3rd year students mostly. Okay, where is this? Right there. And the name, please. One thing I'm going to tell you one more time. Put the names in the file save management. Do not do all your work. And at the end, you create 2 files. One of them is the part file. The other one is the analysis file. Try to rename it there, because we are used to doing this thing. And we make a Word file at the end. We say, oh, I know the name of the Word file. I want to change it. So you go right click, rename, and put the new name. Or even worse, you open it up and say save as something else. That does not work in CATIA. You can do it, but when you send us your work, your analysis file cannot find out where that part is, okay? Because you renamed it. It doesn't know that. Use file save management. So your ID number 1, 2, 3, 4, 5, 6, 7, 8, 9 dash. Your last name. I'm going to upgrade you from Timoshenko to Euler. Euler. This is your last name. Homework, let's call it homework. No, it's not homework. What is it? Let's call it problem 1. How about that? Problem 1. Okay. And any other identifiers that you think is going to help you add it here. So I'm going to say this thing with sketch, because I'm going to come back and with sketch, I'm going to come back and do this thing using with wireframe with a sketch. Okay, good. Okay, and okay. Do not come back at the end and right click and rename. It's not going to work. Okay, good. So let's make it. So what are we going to make? We're going to draw a line basically, like this. Okay. So on this vertical plane, I will sketch. It's not quite a line, so it's going to be something like that. I'm going to put the dimensions in a second. Let's recall what these dimensions were. So the distance from here to here in the problem that we did was 8. Okay. And the distance from, I think, there to there was, if I'm not mistaken, 5. And this radius was 1. Okay, exit. This is it. This is your part. Don't try to make 3-dimensional object out of that. One of the nasty things that we do is that we give a drawing which looks like in 3D, And people who are not, basically with us, they just show up the last few days of the course before the test. They see a three-dimensional object, and then they're going to make it like that, and then they're going to measure the solid element. No, no. If this problem was given to you and says use the most appropriate element, it's the beam problem, and this is it. This is your geometry. Don't make a three-dimensional object out of that. Okay. Now, the one thing that you should not forget is when you created the sketch. You see, I created the sketch. That's what I did. There it is. This is a sketch. Join it. Without joining it, the next step when you go to the analysis is not going to work. Okay. So how do you join? Join is in the generative shape design. This icon. It's this icon. See other operation. It says join. See that? Join, join, join. You select it, and it joins it. Without doing this thing, you cannot solve the rest of the problem when you go to the analysis. Now, let's apply some material to it. Where's apply material? Metal. Let's make this thing out of steel on that part, and it's okay. And it's right there. You can see that. We save this thing because we are done here. We are done here. Now, we're going to go to the next step, which is generative structure analysis right there. And in the past, every time we went there, you saw a three-dimensional object, and it immediately meshed it. There is no three-dimensional object here. This is just a sketch in space that you did. You didn't do any meshing. You have to do that. So in this toolbar where the traffic light is, Model Manager, this is the three-dimensional object, three-dimensional element. This is the beam element. In between, we're going to come and do it next week. Okay, these are called shell element, pop can, propane tank, the hull of a ship and things like that. You do it with this. It's a beam element. That's what beam measure. You select it, turns yellow, and what this element size is, remember, you break it up into little elements, one-dimensional element. So that's the size. So if you say 1 means that one of these elements is going to be 1, 1, 1, 1, etc. Okay. Now, if this radius is 1, this is going to be a terrible probably element here because this whole radius was 1. So I leave. I'll change it to 0.5. At least I track some of the curviness here. Okay. Let me make it 0.3. Now, the other thing that even if you're not here or you're not paying attention, if you use parabolic one, CATIA will not run. It comes back and say Elfini is not supporting that element. So I don't know why the heck they put it there if it's not supporting it. Okay. So this one is the one supposedly more accurate. I could not get it to work here. It comes back with a message saying that this is not supported. Okay, fine. Then we have to go back and do it with linear type. Is there a question?
Yeah, can you please repeat how to join the line? I missed that step.
Okay. Cancel that. Kill that. You're down here. Once you create your sketch, you need to join it. The join, you're not going to find it. You're not going to find it in part design. You're not going to find join in part design. You're not going to find it there. You have to go to generative shape design, or for those of you who remember some stuff from last year, there's something there called wireframe and surface design. You can also join it there. But look, just go to generative shape design. Right there. See the join? Join, select it, and select the sketch. That's it. There's nothing to it.
Thank you.
There's nothing to it. Yeah. Now go to back. I'll take you back to generative structure analysis. You're doing a static analysis, a beam measure. Select this, and I change that thing to 0.3. And I told you why, because this radius itself was 1. So if I measure it with one element of roughly size 1, probably it puts a straight line between these 2 points. All right, I made that 0.3. Good. Now the mesh is there. You can see that, and you can even look at it. There's nothing exotic here. Right click, mesh visualization, say okay. Just zoom in, see what happens. Zoom in, Zoom in. Here is element number 23. It goes between nodes 1 and 25. Here is element number 22. It goes between 25 and 26. Nothing exotic like a three-dimensional stuff that you see. So deactivate it. It's there. Deactivate it. Now, you have to tell the software what is the cross-section. So notice that we never paid attention to these guys because when it did it for us automatically with 3D element, it automatically used 3D property. Well, we didn't do it here, so we have to use the 1D property. Look, there's an I-beam here, the shape of an I-beam. Can't forget this. So if you want to specify the cross-section of the beam, the one that has an I-beam. Okay. Now, there are different ways of, there are different things you have to do here. First of all, the support is that join. If you had not joined this thing, you will not be able to mesh, you will not be able to reach this thing. Now, notice that for the other class that I did, it was a rectangular beam. This is why this looks like a rectangle. So I'm going to change that to circular or cylindrical. And notice that, well, where's the cylinder? Where's the circle? Well, that's because the radius of it is 0 right now. If you click on this wrench, you specify the radius of the cross section, which in this problem was what is that? Radius, cross-sectional radius is 1. Okay, so so there we are. So you put a 1 here, and suddenly you see a big fat circle appears right there. That's the way it should be, right? Even when you did three-dimensional element, you drew a circle here and then swept it or ripped it like that. It looked like this. But these are beam elements, and the reason you see 3 of them is because your sketch had 3 parts. This part of the line, that part of the line, and that part of the line. Okay, that's why it shows you 3 of these. And notice that you can close it. See, you say, okay. If it's anything but cylindrical beam, if the cross-section is anything but circle, you cannot close it. It's expecting you to go and select the orientation point. Not here, though. That's okay. There we are. This is as exotic as your figure is going to get. This is it. It's got all the information in it, but this is as nice as it's going to get. Okay, so let's save everything. File, please use save management. Save analysis, save as. I move it out here so that I can see what I called my part. My part was called like that, so I give it that kind of the same name. I say your ID number 456789, your last name Euler. The problem that you're doing is problem 1. With sketch, right? The only reason I'm making this exactly the same as that, so that you come back, you know what problem you're doing. And then analysis 1 is fine. Okay, now, we know the bottom of this beam is clamped. There's your clamp, good old clamp here. You know that that top point is subjected to a force in the x direction of 2,000 pounds. That's the way it was. So this is done. Force is right here, right there. Force, distributed force. On that point, in the direction x minus 2,000 or 2,000, it doesn't matter. Get rid of this y. That's the way it was, wasn't it? That's the way it was. Say okay. And save it. Run it. Always pray. Finished. So, how does it deflect? Isn't that the way it's supposed to be? Let me zoom in. Isn't that supposed to be? This thing should bend. You can see that it's bending. This vertical piece should bend and twist, and it does. We can't see the twisting because it's shown like a line. You can see the twisting, but it is. Okay. Now, do you want to see the amount of displacement? There is the amount of displacement. This was called deformation. This is called displacement. That much. If you zoom in closely, you see that these are all little arrows. Each node goes by that much in that direction with these amounts. Okay. If you want to see the contour plot or contourish plot, you say click on it, average ISO, and there we are. Some people prefer this over the other one. Okay, good. Now, the bad news is that CATIA's beam bending models do not give stresses. There we are. You cannot plot von Mises stress. You can plot something called principal stress right there. See, I open this up with the displacement. The second item is principal stress. The only unfortunate, you know what a principal stress is? The only unfortunate thing is that it gives you the principal stress at the axial stress. Totally useless. Now, when I did this, let me ask you this. When you did these hand calculation problems for Dr. Green, either in deformable bodies or stress analysis, if he wanted you to give him the stress, he would have to give you one more piece of information. Okay, give me the stress. There must be something else that he said. Can somebody tell me what would you just say it? I can't go to the chat, please. Just say it, one of you. Give me the stress. What else he has to tell you so that he doesn't have to mark 50 different answers?
At what location?
Exactly. In other words, yes, give me the stress at the top fiber, at the bottom fiber, halfway in the middle, at the center. So to expect CATIA to give you stress, it's foolish, because before there was no issue when we were doing with solid elements, you could find the stress anywhere. But here, the stress, you have to say where. Now, some other software will plot you von Mises stress, for example. But then you have to go and read the documentation. Is at what location did they calculate this? Okay. For example, they might say center at the neutral axis, it's the top fiber, it's the bottom fiber, or you can even go and say where you want it, you input it. But don't be fooled. In other words, do not expect to get stress distribution like before just by saying, give it to me, because you have to say where. This is why they don't have it here. Now, having said that, I remember yesterday I was accidentally looked at the chat of the people, what they were saying. Somebody said, this is useless. What good is that? What good is displacement going to do? You're absolutely right. If you want stress distribution in the beam, don't count on CATIA. Now, there is a reason for that. Let me just spend maybe 30 seconds tell you what. CATIA is an excellent CAD package. It's not that good a finite element package. For the kind of things that you have in mind, we have in mind, it's good. For 90% of the stuff that they do in industry, maybe that's exaggeration, 80%. So for 80% of the stuff that they do in industry, people get paid, they design things, they make things, it's good. But if you want to kind of get very detailed information about your part behavior, it's no good. Let me give you an example. When you design a part for a car, you don't want it to yield, right? So all you want to do is you make sure von Mises stress is below the yield strength. That's it. But if you're stamping a part, you want the part to yield. You want the part to change shape. So those are, let's call it, advanced applications. For 90% of the people who do work in engineering, for private sector companies, they want to design so that it doesn't change shape permanently. That's it. Anyway, yes, I'm sorry. This is not a good package for beam in particular. Okay, so let me save this. Now, I'm going to kill that, and I'm going to repeat this problem, not with a sketch, Incidentally, notice that there are two joints here because the second time the fellow asked me how to do it, I joined it again. Let me get rid of this. There's two joints. There should have been only one. I joined it the first time, then I went and did it again, created the second one. That's fine. Now, I am going to save this thing with a different name. File, save management, save as. This name, I don't want to call it with a sketch. I'll call it wireframe. Wire. Very good. Okay, good. Everything is the same, except that I don't want it sketch. Delete this. Delete the sketch. I've got nothing there. So now I'm going to make the part, which means that line for me as a collection of points and lines. So here's what I'm going to do. So let me create 4 points. I'm just doing this thing on the fly right now, so be patient, please. One is 0, 0, 0 right there. This is 1 point. Then I'm going to do one that goes all the way up to 8, 7. 7 inches up. You see what I'm doing. Then I'm going to create one that goes 1 to the right of this, okay? 1 to the right of that, and is going to be. I'm sorry, did I say 7? Okay, so that hang in there. Yeah, 7. That's good. Okay, so 1 to the right of that. So you'll see what I'm doing in just a second. There. Another one going up. You might say, why the heck are you doing this? You could have done it as a sketch. You're absolutely right. That's what I want to show you. 8, right up there. And another one, which is, let me remember, this was 5 inches. So that's another 4 inches to the right of that. 4 inches to the right. I know that you may already be lost, but be patient. Be patient. Look. A line going from here to here. This is not a sketch. This is a line. What I just did for you was to draw from here to there. And then I'm going to do another line from here to there. And then I'm going to do a circle in space with that center, etc. So here we are. So another line from here to here. Perfect. And now a circle centered there, and for example, passing through these 2 points. So let's see that. Look at the way you make a circle, and there are different ways of making a circle. For example, you can say center and radius, center and a point. Okay, fine, center and a point. There's the center, and there's the point. And I don't want to go 180 degrees. I want to go 90. Hopefully, they'll give it to me. And there's something else. Support is this plane. Okay, so this angle is not very good. So I go to, let's go from 90. I have to play with this thing a little bit. Come on, 90 to 180. 180. I'll make it work. Don't worry. Going the other way now. Okay, so let's just fix this. Here you got to think a little bit. You know what? Maybe we should do a different way. Different way. Cancel that. Cancel that. Let me create another point which is over right in that corner. So so let's see. Maybe x is 0, y is 0, 0, and z is 8 right up there. And now create a circle. 3 points. Where's the 3 points? It must be 3 points. 2 point and radius. 3 points. Yeah, 3 points. Very good, very good. So here and here and oh, wait a minute. Damn, that's not right. 3 points. So I dug my own grave here. So let's see now. Center and radius. Okay, let's do this. Center and radius. That's better. Here's the center. Radius is 1. The support is this plane. Okay, is that the right one? Okay, and I don't want to go from 0 to 180. Let's go from 0 to 90. No. So go from, what was this one? Was,
Sir, it's 180. 180. Okay, you got it. And
that
200.
again?
I think it's 180 to 100, 200 and
70?
or 90 to 80. 90 to 180.
Look, I think this is doing it, right? 180 to 270. No, I'm sorry, say that again. Now I have to, you said 90 to what?
180.
180. Excellent, thank you. Was it worth it? No. Why do we have to do this? Because not every beam is in a plane. This was all in a plane. But if I had a helix, there is no way you can put a helix in a plane. So you cannot do it as a sketch, as simple as that. Okay? Anyway, yeah, there we are. This is my model. Okay? And these points they're going to stay there. I don't care. Join it. Join it. Join it. This sketch, or this curve, and that curve, and that. These are not sketches. These are wireframes that you created. You have to join, otherwise you cannot do the rest of the problem. So the rest of it is the same. Save this thing. Now go to generative structure analysis. Static, beam, select this. 0.3, we're going to use the same numbers. Now, what I suggest is you hide these points, because eventually I'm going to clamp this and I'm going to clamp and apply force here. But if you put the clamp on this point instead of the end of the bar, which is called the vertex, or if you apply a force on the point instead of the end of the bar, end of the line, which is called the vertex, CATIA will take it. But when it runs it, it does not see it, and therefore you don't get any deflections at all. This is why it's a good idea, any geometrical entities that may interfere with you, hide it. Those don't bother me, okay? Those don't bother me, so I'll just leave it the way it is, okay? Now, clamp the bottom, apply a force right there. It's the same numbers. Let me show you, if I run it, what kind of error message you get. First of all, let's save this thing. File, save management, save as. Just use the old analysis, except that instead of saying, is this the old analysis? Oh no, cancel that, cancel it. I'm choosing selecting the right one. It's analysis, save as. Just use the old one, except don't say sketch, say wireframe. Wireframe. Say okay. There's something that I haven't done, and because of that, I will get an error message, and I want to show you. I want to show you what that error message is. You see, acquisition of field model failed. I don't know what the heck that thing means, but it says could not find any property. Check your model, because we did not say what the cross section looks like. Listen, a lot of these error messages are totally useless, because people who write software, they're not good communicators. So 1D property, select that. Nothing has changed. The radius, the cross section was circular. The radius is 1, so everything is the same. You can see that, yeah. And now you run it. It was a good idea to save and then run, in case I have to kill it. I don't have to kill it. Okay, so there we are. I can see that. It's the same thing as before. As I said, you might say, well, no, this thing took you 7 more minutes, and somebody had to help me. I agree with you. I could have done this thing with a sketch. However, if your structure does not fit in a plane, you cannot use it as a sketch. Okay, so before I do a little bit more about this problem, are there any questions? Is that a no? Okay, So let me go get my first one. The first one was, what was it? It was the Euler part, right? Part 1, I think it was right here. This is very good. This is the first one that I did with a sketch. I had 2 joins. Let me delete one of these joins. Okay. That second join was totally useless. Let me save it with a different name. File, save management, save as. It is a sketch, but I will say rectangular cross section. Rectangular X section. How about that? So no longer a circle, but a 1x1 rectangular cross section. You know, actually, to make it to make it visible on the screen, I'm going to assume that the cross section is a rectangle, but the size of the rectangle is not 1x1 or it's not a square. It's 2 by 0.5, so you can see things. Okay. So let me create 3 points. Let me create 3 points. Well, I didn't do these things for you. This is the first time you're seeing beams. So I'm going to create 3 points. You will see why. I'm going to create 3 points. One of them is x of, let's say, make it 1. Let's make it x of 1. Right there, you can see that. Let me make it a little bit longer so that you can see it. So maybe 3 so that you can see it easier. Good. Another one. This time, x0, but y of 3. It's going to be there. You can see that. And a third one, which is 3, 3. I created 3 points for you because I want to show you what happens when you say that the cross section is a rectangle. You can't close it. You have to select the orientation point, and then you see what happens. Okay, so this is saved. Now we're going to go to generative structure analysis. Static, nothing exotic. You do the meshing. There we are. This should turn yellow, by the way. If it doesn't, means that something is not working. It's not going to do it for you. Now, 1D property. There we are. 1D property. Click on it. Not circular anymore. I'm going to make it rectangular. And first of all, the support is right here. You can see that. The support is this. Notice that as soon as you select the support, it knows what the material is because it takes the joint basically and knows what joint material has. Rectangle. Click on the range to specify the size. And I'm going to make it 0.5 for Y and 2 for Z. I hope somebody will ask me at the end, what is this Y and Z? What are you talking about? We'll get to that. For now, just look. There we are. It won't let me close it. Look, I can't say OK. Because it's expecting me to select an orientation point. So I select the orientation point. Let me start with the first one. Remember I created 3? Let me select this and watch that those red rectangles. Look at what happens when I select it. So what happens is that your rectangle, you know, over here it looks like that, and it goes up here, and then it goes like that. This is not what I want. Okay, let's try another one. Instead of this, try that. Oh, maybe this is what you want. Yeah, you see this? Rectangle, rectangle, rectangle. Keep staying normal to that spine, and then go like that. Let me try another one. That other point, the third one that I created right there. Yeah, some jumbled up thing. The moral of the story is this. The one that in all likelihood you had was this guy. Now, by the way, I can make this thing to be, I don't know, 2 and 2, so you see it a different way. Right there. See this? Now, somebody says, well, do we do these things randomly? The answer is no. There is a process behind it. One thing you know, if it's a circle, you don't have to worry about this. You can close it. But there is a process behind it, and things like this, one really should go to the documentation of CATIA and read it. There we are. So notice that it's talking about Y and Z. This Y and Z is not that Y and Z. The Y and Z you see up there in the global system is not this Y and Z. So what are these? Well, I think I took this one as my orientation point. Let me, I can't remember which one did I take as the orientation point. Oh, this one right here, right here. So the way it works is you says, okay, my X is always along the path. That's the way CATIA works. The X is always along the path when it comes to this dialog box. Then you drop a perpendicular from this point that you select to the path. Therefore, this point cannot be on that path for sure, because you're going to drop a perpendicular. That perpendicular is called direction Y. In fact, you can see it. Look at the axis system. This is Y, right there. You see this? Drop a perpendicular from here to the line. That is your Y. Z is perpendicular to the X and Y, and that determines everything. If it's a circle, don't worry about it. You can close that. All right, I've got 2 minutes, 2 minutes left. So are there any questions? So this video, like this lecture, like any other lecture, like any other presentation, like any other homework, is going to be taped, recorded. The homeworks, I will not post them. The solutions, I will not post them on Blackboard. You already know it's on YouTube, and I'm going to do the same thing for the next homework. Okay, yeah. The best thing that you can do for yourself for preparing for the test is, first of all, save properly. Okay, save properly using file save management. It's so tempting to say, I don't have time to do that. Let me go and do everything with part 1, analysis 1. At the end, I'm going to change it. You can do it, but not the way you change Word files and PowerPoint files names. Okay, you can do that kind of a thing by going to the file save management, take the one that default, bring it, and then put your ID number, blah blah, and save it. The problem is that people usually do these things the last minute when they're supposed to submit their tests, problems, and they panic, they make mistakes, etc. This is the first thing. The second question was, I think different sections is, how do we prepare more for whatever we want to do? I don't know, test. Well, look, you have the opportunity to look at the other 3 sections. When I say the other 3 sections, because you probably, maybe you belong to lab 51. There is lab 52, there's lab 53, and there's lab 54. Their problems are different from yours. They may look the same, but there are some minor changes. Well, look at their problems. The solution is up there. That's, what else can I do for you? Okay, folks, are we good? It's 1:51. Let me stop recording this.